Hello, everyone. I'm Ting Yuan from Institution of Computing Technology of the Chinese Academy of Sciences. I want to share with you today is GoBench, a benchmark suite of real-world Go concurrency bugs. Let's introduce it from the beginning. Go is an open-source programming language designed by Google. It is growing rapidly and has been used by many developers. As can be seen from the following two figures, compared with other new languages, the number of developers who are using Go and who want to learn Go is the largest. In order to cooperate with modern multiple computers and facilitate concurrent programming, Go provides many new concurrency primitives. The most important two are coroutine and channels. A coroutine is a function that's capable of running concurrently with other functions. To communicate with each other, coroutines use channels to pass messages. Do not communicate with sharing memory. Instead, share memory by communicating. This is the sentence strongly promoted by designers of Go. But the real-world Go applications, channel-based message passing, and mutex-based shared memory are both widely used. These mechanisms not only bring convenience, but also make users more likely to make mistakes. In this figure, the two coroutines are using an unbuffered channel, namely pod chain, and a mutex, namely pod lock, to synchronize with each other. Coroutine 1 performs a reception by pod chain. Next, lock and unlock pod lock, and then repeat the above operations. Coroutine 2 sets true to pod chain in the critical section of pod lock, and also performs the same operations twice. As you can see, following the scheduling sequence indicated by the red arrow, the program will exit normally. If we change the scheduling sequence, like the red arrow in the figure, a deadlock could occur. Coroutine 2 first grabs the pod lock and then waiting for a receiver of pod chain, but the only receiver, coroutine 1, is acquiring pod lock to continue its execution. As a result, both coroutine 1 and coroutine 2 are blocked at the read instructions. In addition to blocking bugs, there are also many Go-specific non-blocking bugs, such as misuse of channel and misuse of alarming function. For examples, the left figure shows us a data race caused by channel misuse in ISTIO. If coroutine 2 closed the downC channel, and then set downC to nil, when coroutine 1 tries to receive data from downC, the data race could happen. The right figure shows us a race condition in anomalous function in CrocRoachDB. Within the for loop, the value of C may be non-deterministic in children coroutines, because the start time of children coroutines are not graduated, and they are very likely to have race conditions with the range statement. Go concurrency bugs have attracted widespread attention from researchers and developers. Researchers on Go concurrency bugs gradually rise in recent years. At the same time, many open source tools have been proposed, such as GoLeak, GoDeadlock, Dingo Hunter. But so far, there is no measurement to evaluate those concurrency bug detectors. Therefore, we proposed GoBench, a benchmark suite of real-world Go concurrency bugs. GoBench is composed of GoReal and GoKernel. GoReal is a collection of Docker files which are easy to reproduce real-world bugs, while GoKernel is a collection of small test functions which are easy to run by Go test command. At present, GoReal has 82 representative bugs found in 9 popular open source applications. GoKernel has 103 kernels extracted from GoReal at a recent study. Let's discuss GoReal and GoKernel separately. GoReal is designed to collect concurrency bugs from the real-world Go projects, such as Kubernetes and etcd. The selection of these projects is manually based on the number of GitHub stars. We search the pull request of these projects to find Go concurrency bugs. A valid pull request should satisfy the following 3 conditions. Firstly, it should certainly address a concurrency bug. Secondly, the reproduce steps should be clear. Finally, there should at least one test function as the entry point to trigger the concurrency bug, so every bug in GoBench can manage it by a unified format. As a result, we obtained all information about reproducing a bug. And then we add it to GoReal if we can reproduce the bug locally. For more convenient importing, we record the reproduction process in the Docker files. By building Docker images, all software dependencies required to run the test function will be downloaded. Then users can run the test function in a container to reproduce the corresponding bug. Please note, these test functions are purely written by developers. At present, GoReal has 40 blocking bugs and 42 non-blocking bugs. Blocking bugs consist of resource deadlock, communication deadlock, and mixed deadlock. Resource deadlock are all caused by logs, including classical ABBA deadlock and double locking. Communication deadlocks are all caused by channels or conditional variables. The misuse of context library in Go is also contribute to communication deadlocks. The mixed deadlock is caused by misuse both of logs and channels. Non-blocking bugs consist of traditional bugs and Go-specific bugs. Traditional bugs refer to bugs that may also exist in other languages, such as data race and order violation. Go-specific bugs refer to bugs that can only exist in Go, such as misuse of channel and misuse of anonymy function. GoKernel is composed of some small and independent test functions. We reconstruct 36 bug kernels from the documents published by a recent study, and extract 67 bug kernels from GoRail. When extract bug kernels from GoRail, we will carefully refer to the text description and the backtraces provided by developers in the pull request, like that. These descriptions and backtraces can help us understand the root cause of the bug, so as to help us keep the same root cause in the bug kernel. We manually extract the code snippets into a separate test function. During extraction, we simplified the code snippets from 3 aspects. Firstly, remove unrelated code, such as unrelated data flows and control flows. Secondly, abstract data structures to a simpler but sufficient format. The type of each field is simplified to Boolean or empty structure. Finally, last but not the least, we preserve call traces to replicate the complex bug-inducing scenario. At present, Go kernel contains 68 blocking bugs and 35 non-blocking bugs. We not extract all bugs in GoRail to kernels, because some bugs in GoRail may use more than 10 unique goroutines, or have complex interactions with other goroutines involving RPC or reflection library. We evaluate exist detectors on blocking bugs and non-blocking bugs in GoBench respectively. For blocking bugs, we apply a static tool, namely Dingo Hunter on Go kernel. In addition, we evaluate both GoRail and GoKernel with the 2 dynamic tools, namely GoLeak and GoDeadlock respectively. For non-blocking bugs, we evaluate the built-in race detector, donate GoRD. For blocking bugs, we summarize the result of the 3 tools in such a table. GoLeak and GoDeadlock both have 28 false negatives. The difference is that GoLeak reports 2 incorrect reports and GoDeadlock reports 7 incorrect reports. The incorrect reports generated by GoLeak are mainly due to the fact that GoLeak cannot distinguish between normal goroutines and deadlocked goroutines. Even if back-end goroutines, such as logger or monitor, are excluded, GoLeak may still report goroutines that are not related to deadlock. The main source of false negatives is that GoLeak's detection is performed at the end of the test function. If the test function has been blocked before return, GoLeak will not work. The incorrect reports of GoDeadlock manually come from the design flaws. GoDeadlock reports every inconsistent log pairs, but failed to check whether they are protected by other custom serializations. The false negatives of GoDeadlock manually come from the inability to detect communication deadlock. On the bottom right side of the table, Dingo Hunter only reports one channel-based communication deadlock. This is because Dingo Hunter needs more engineer efforts and does not have ability to detect log-based deadlock. For non-blocking bugs, the built-in race detector performs pretty well. The false negatives are manually due to the order violations in the user programs or standard libraries. We also apply dynamic tools on GoRail and GoKernel respectively, and record the first time a tool reports a concurrency bug. The result shows that dynamic tools often require many times to report bugs. The best performer is GoLeak, which reports bugs almost the first time if it can find bugs. But GoLeak may report thousands of possible deadlock routines at once, which requires further manual efforts to filter out which routines really involved the deadlock. In GoBench, there are also some bugs difficult to be detected by exist detectors. For example, serving 2137 is a mixed deadlock bug that is difficult to capture. This bug spans multiple routines in a for loop and involved multiple buffered channels with different buffer size. Currently, no static tool can model such complex situation well, and due to the large space of intervening, dynamic tools usually need to run tens of thousands of times to trigger the bug. You can try its bug kernel in GoBench following this link. In conclusion, GoBench is the first benchmark suite of real-world Go concurrency bugs. Current tools cannot achieve perfect detection results. Static tools need to improve the effectiveness of finding concurrency bugs in Go, while dynamic tools need to improve the efficiency of finding concurrency bugs in Go. At the end, we open the source of GoBench on GitHub. We believe GoBench will be instrumental in helping researchers understand concurrency bugs in Go and develop more effective tools for their detection. That's all. Thank you.